Welcome you all. Today we start our article 3.6 where we discuss delta function, functions and mixed random variable. Now so far our analysis of continuous random variable parallels our analysis of discrete random variable that we discussed in chapter number 2, if you remember. Okay, because of the different nature of discrete and continuous random variable, we present the probability model of discrete random variable as a, if you remember, as a PMF, probability mass function, and we represent the probability model of continuous random variable as a PDF. Okay, so if I write here for discrete we use PMF, for continuous we use PDF. Okay, now these functions are important because they enable us to calculate the conveniently parameters of probability models such as expected values and variance and probabilities of events. So in this article we introduce the unit impulse function as a mathematical tool that unites analysis of discrete and continuous. So we use delta function as mathematical tool that unites the analysis of discrete and continuous random variables. So the main idea is that we want to unite these two analyses. For that purpose we use that delta function. Okay. The unit impulse often called the delta function allow us to describe calculation with both types of random variables, that is continuous and discrete random variables. So important thing is due to this we have a mixed random variable. So what is mixed random variable? Which have which has properties of both continuous and discrete random variable. So what is mixed random variable? Mixed random variable is the one uh, which has properties of both continuous and discrete random variable. So delta actually help us uh, to define the mixed random variable. Now let's start with the definition, and definition is 3.12, and it says that what is unit impulse or delta function. Normally we say that we have a function d epsilon of x is defined as 1 over epsilon, whereas the x value varies from minus epsilon by 2 up to epsilon by 2 positive side and 0 otherwise. So this is the definition of d of epsilon. And now the unit impulse function is that we say that delta of x actually is equal to limit when epsilon is tend to 0 d epsilon of x. So this is the definition of delta function. So we also know that if we integrate delta from minus infinity to infinity, delta of x d of x, this is equal to 1. Now this is a property of delta function. So if you look at how this look like for d function, if we have this axis that is represented by x, and if this is our delta function, okay, delta of x. Now if we look at d function, so if this is minus 1 by 2 and this is 1 by 2 in terms of epsilon, in that case epsilon is equal to 1. Okay, if you increase the value of epsilon, let's suppose you say that epsilon is 1 by 4, so this is the range you get. If you further reduce it, say 1 by 2, so then d function is look like this, and so on. So means that as you decrease the values of epsilon, it will approaches, this function will approaches the delta function. So this limit tell us this thing. Actually this limit explain this thing. As you goes epsilon up to 0, it will approaches the delta function. So let's do some theorem. So these things you already go through in signals. So let's discuss this theorem 3.16. So it says that for any continuous function, for example g of x, if I take limit minus infinity to infinity, g of x delta of x minus x naught dx is equal to g of x naught. So this is also known as shifting property. So this is also known as shifting property of delta function. Now we defined 3.13 another important function which is known as unit step function. So unit step function is easy to realize and easy to use, that will be when we do the analysis. So the unit step function is defined as u of x is equal to 0 and 1. 0 when x is less than 0 and 1 when x is greater than or equal to 0. And there is a theorem that relates delta and unit function as Theorem 3.17. It says that if you take the integration from minus infinity to x, delta of x, delta v of d of v is equal to u of x. So this theorem relates, if you take the integration of delta function, you get the unit impulse. So, or in other words, if I want to calculate the delta function, I need to differentiate the unit step function, okay, for unit impulse. So so the main idea here is that if we using the definition of unit step function, we write CDF of x. Definition of unit step function. We can say that CDF summation, so we are talking about the discrete random variable. So this is for discrete case, okay. So we can say that this summation that x I is belongs to range of sampling space for random variable x. Let me rewrite it here. So this is equal to PMF x of n times u of x minus x. So this will, because of the property that it will take, so this is the way you can write the CDF. So if I want to write the PDF, so from definition, as we know that if you look at the definition 3.3 in your book, and 3.3 tell us that what is the relation between CDF and your PDF. So if you recall the definition, so let me write the definition here so that you understand it. Definition says that fx of x, that is the PDF, is equal to derivative of CDF. Okay. Now if I use this definition, and I know that delta is actually derivative of u of x, so from here, so this implies that if I take the derivative of this, if I apply that, okay, fx of x is equal to, if I apply this on equation 1, what happened? So this becomes summation xi belongs to sx, and PMF is written as it is because this is just a number, but when I take the derivative of a unit step, so it becomes a delta, so it can be written as delta of x minus xi. So this is the first relation that relates your PDF with the PMF. So this is very important relation. So if I plot it, this becomes x. If I look here, if this is my PDF, so this becomes a PMF. For example, x of I. This is xi. Let's say this is x1. Okay. Similarly, px of x2 is x2, and so on. So this is the way you can write PDF in terms of PMF. Now if we look at so we know that what is expected value. Now expected value is defined for if x is a continuous random variable, and we know that this is equal to minus infinity to infinity x time PDF. This is the definition of expected value. Now as as we know that PDF we wrote like summation xi belongs to s of x, okay, px of xi times delta of x minus xi. So if we apply this definition to this one, so this is for continuous case because of the PDF, so we can write the discrete expected values as in terms of integral from x time summation xi belongs to s of x px of xi times delta of x minus xi dx. So this is another formulation that we can use PDF. Okay, expected value we can calculate in terms of integral as well for discrete case. Now to clarify ourselves further, if we rewrite this and take the summation out, because integration can be interchanged with the summation, so summation becomes outside, that is xi belongs to s of x minus infinity to infinity x times px of xi times delta of x minus xi j dx. So if we do the integration, so these becomes numbers, okay, these are numbers actually, okay. When we do the integration, so what happened, these numbers actually the integration of delta becomes the unit step, and when unit step means the values that is greater than 0, so this can be written as summation of xi belongs to sx x of I p x xi. So because this is number, when you multiply delta with this thing, this gives you xi, okay. So this again become number. When you integrate a number, so it gives you when do it from minus infinity, it gives you 1, so it is multiply 1. So this means that these formula are consistent for discrete random variable. These formula for discrete random variable. So this means that delta and step function can help us to write or interchange these two formulations. Now to clarify this, let's consider an example. Example is 3.19, and in this example PMF is given to us of a random variable y, that is 1 by 3 when y is equal to 1, 2 and 3. 0 is otherwise. Now similarly CDF is also given to us, that is Fy is equal to 0, 1 by 3, 2 by 3 and 1. 0 is when y is less than 1 and 1 by 3 when y is between 1 and 2. And when it is between 1 and 2 and 2 and 3 is 2 by 3. And it is 1 when it is greater than 3. So this is the formulation we get. Okay. Now question is how we can represent these using these delta and unit step function. Now for CDF we can write CDF as, so for first one we know that this is can be written as 1 by 3. So this value is at 1, so we can write u time y minus 1 because it take this 1 by 3 to 1, plus the second one is at 2 is also 1 by 2, so we also write 1 by 3 u of y minus 2, again 1 by 3 u of y minus 3. So let's look at graphically what happened. So as we know that u of y is defined. This is your u of y. Okay, 1, 0. This is the y values. Okay, so this start from 1. So this is your u of y. Now if I shift it, u of minus 1. So u of minus 1. Let me give another color. It will start from here, start from 1, goes up to infinity. So this is your u of y minus 1. Okay. Similarly, if I look at u of minus 2, it will start from 2 and goes further. So this is 2 u of y minus 2. Similarly, for u of y minus 3, it start from, let me use different color, goes, so this is at 3, so u of y minus 3. Now if I add these 3, okay, so if I add these, so this equal to, if I add these 3, so not the one with u, but if I add u of y minus 1 plus u of y minus 2 plus u of y minus 3. So what happened? Now look here. U of y minus 1. Similarly, similarly 3. When I add these 3, so till 1 is 1, let me write with red one. So it will start from 1, goes up to here. Now these are 1, it becomes 2. Assume this is 2. So till here it becomes 2. Now it becomes 1, 2, 3. So it moves further up to 3. So this happened. This is 1, this is 2, this is 3 when we add these 3. Okay. Now we can use this to represent the CDF. How we do that? Let me plot this CDF. Now if I plot this CDF, so it becomes, it says that less than 1 is 0, so this is 0. At 1 is 1 by 3 till 2. So assume that this is my, sorry about that, this is my 1 by 3. Okay. This is 1 by 3, and is 1 by 3 till 2. Okay, so till 2, so this is 2. After 2 to 3, so this is my 3, it becomes 2 by 3, so assume that this is 2 by 3. This is 2 by 3, right? Now after 2 by 3 it becomes 1, so after 3 it becomes, so assume this is 1. Okay, so this is my CDF. Now I want to make it from this one, so look here. First I need 1 by 3 at 1, so it is 1 at 1. Now I have to multiply with 1 by 3 so that it becomes 1 by 3 at this point. So if I multiply this with 1 by 3, okay, so when I multiply this with 1 by 3, so it will start at here, goes there. This is 1 by 3. Okay, now after 2 again I multiply by 1 by 3 because it will goes up. Now here till 2 is 1 by 3. After that we have 2 by 3. Now this is 1 by 3. Now if I add 1 plus 1 by 3, it becomes 4 by 3. Now we need 1 by 3. So if I multiply with 1 by 3, so it becomes 2 by 3. So that is 2 by 3. Okay, this is 2 by 3. We'll start here. Now after that again we need because this is already 2 by 3, how much we have to add is 1 by 2, so it becomes 1 by 3 again. So this is the way we can represent using step function. Okay, so we can represent this using step function. This is the way if we look at graphically. Now let's move to next one. So the PDF of same example, if we look at the PDF of y is, so it becomes, as we know that PDF is just derivative of CDF. As you know that CDF that we already write in previous was 1 by 3 u of y minus 1 plus 1 by 3 u of y minus 2 plus 1 by 3 u of minus 3. So this is my PDF. When I take the derivative, so it becomes, PDF becomes, instead of delta step, you have a delta function here. Because this is a constant, you have to take the derivative of step function. That becomes the delta. So this is the way, sorry about that, this is the way you can write your PMF, PDF and CDF in terms of delta and step functions. So this is the solution. Now after that we calculate the expected value of y. So if you remember, the expected value of y is minus infinity to infinity y f y of y. So we already calculated. Now just plug in the values, so it becomes minus infinity to infinity, okay, y divided by 3, right? So it becomes delta y minus 1 plus delta y minus 2 plus delta y minus 3 and dy. So we know that when we take the integration of the delta, it becomes a step, and step integration from minus infinity is 1. So this implies, as we know that this becomes, because this is multiplied with y, so if we apply the theorem that says that when we multiply with y with delta, it gives you values at that point, and when we do the integration, it will be the same value. So it becomes, so expected value of y becomes minus infinity to infinity y by 3 delta y minus 1 dy plus infinity to infinity y by 3 delta y minus 2 dy and plus minus infinity to infinity y by 3 delta y minus 3 dy. So it becomes, for first one it becomes 1 by 3. Okay. So for second one, because it is multiplied by 2, it becomes 2 by 3. For third one, it is multiplied, it shifted to 3, so it becomes 3, so it becomes 3 by 3. That is 1. So when we calculate the expected value of y, so it becomes 1 by 3 plus 2 by 3 plus 1. When we solve it, so this becomes 2. 2 is the answer. So this is a very easy way to calculate the expected value using the delta function representation. Now if you know that when CDF, that is fx of x, has a discontinuity, at x we will use fx of x positive and fx of x negative to denote the upper end and lower limits of x. Okay, that is that we can say that fx of x negative means that we are reaching h from a positive side, and we say that this is equal to fx of x minus h. And similarly we say that when fx is positive, so this means that this is equal to limit we are reaching x from 0 positive part fx of x plus h. So this is the basic idea we use. So in other words, we can say that the CDF has a jump at x naught then PDF has an impulse at x naught. This is important. Weighted by the height after discontinuity. Fx of x positive minus fx of x not negative. So the main idea is that if there is a discontinuity, then we can represent this using the impulse or delta. Now if we look at example here, example is 3.20, and it says that if we look at example 3.19, so in 3.19, if you remember, we have CDF that is written as 0 when y is less than 1, 1 is less than 1, less than 2, 1 by 3, then it is 2 by 3, then it is 1. It says between 2 to 3, and y is greater than or equal to 0. So this was the limit. So look here, this is the jump here because we have different values at 2. If we, this is the jumping, that is telling us the jump. So this means that so this implies that fy of, if you come in from negative, so it becomes 1 by 3, and if you come from positive, it becomes 2 by 3. So that's why it has jump. Okay. Now we understand the jump. Now let's continue theorem here. Theorem 3.18. So 3.18 says that for a random variable x, we have the following equivalent statements. What are equivalent statements? The first one is that probability when cap x is equal to x naught is actually equal to q. The next one is that PMF at x naught is also equal to q. So either you can calculate probability by putting capital X equal to x naught or PMF. Third one is that either you take the difference from x naught positive minus x naught negative, you get the same probability value in CDF. So we just look at the jump and that tell us the probability at that point. And last one is that the PDF is equal to, at that point, is q naught delta of 0. So this is the basic idea, that these are all equivalent statements. So this is very important theorem, and it says that if x not equal to q and pf is equal to, so you can calculate this using these important criteria. Now let's start the important topic here. Now is the mixed random variable. So we have to start with the definition, and that is 3.14, and it says it is mixed random variable. So what is mixed random variable? It says that x is a mixed random variable if and only if I look at the PDF, contains both impulses and non-zeros. Means that if non-zeros and finite values. So the main idea is that if we have these things, so this means that this is a mixed random variable. So mixed random variable has some discontinuity. Now for example, if we have a CDF, if we look at the example here, example has a CDF like if I show the graphically first and then write the equation. So this CDF says that this is with the same example which we did. So this is 1 by 3 and at 3 is 1, assume this is 1, we have a relation like this. So this is the CDF. Now if I look at the mathematical representation, it becomes Fy that is equal to zero, y is less than 0, 1 by 3 plus 2y by 9, 0 is less than y is less than 3. Now and 1 when y is greater than equal to 3. So if I look at the PDF, so because there's a shift here, at this point there's a jump at 0, because it jumped from 0 to 1 by 3. Look here, this is the jump, this is 0, after that it goes to 1 by 3. So there's a jump. After that we have a continuous. So if I look at the PDF, so in that case, if I write the mathematical equation of PDF, so it becomes, because we know that what is PDF, how you calculate, you take the derivative, okay. Now if I take the derivative of 0 is 0, alright. If I take the derivative of this term, so 1 by 3, so derivative of 1 by 3, because this is a constant number, so in that case this gives you value at that point. So this means that if I take the derivative, so it becomes 0. So but at this position, if I do that, so because this is multiplied by 1, as we know that u of x, that we say that is minus infinity to n. Sorry, let me rewrite it. As we know that delta of x equal to derivative of u of x. Okay, and we also know that if I integrate minus 1 to 1 u of x, this is equal to 1, so we can either write it 1, so means that 1 is equal to this derivative. So if I take the differential here, so it becomes delta of y. Okay, if I take the differential here, it becomes delta y. So that's why 1 by 3 is written as delta of y divided by 3. Okay, plus, now take the derivative here, because y is present, so derivative y is 1, so it becomes 2 by 9. This is only possible in this range. Just write the range here, so it is the same range, and we know that if we take the derivative of this and this becomes 0, so put 0 and write here otherwise. So this is the way to write the PDF. Now if I plot this PDF, so it becomes this is y, and we say that this is 0. So at 0, this is a delta function of height 1 by 3. After that, if we look at calculation, so if I put the value 0 here, okay, and it becomes for 0 delta is 1 by 3 and plus 2 by 9, so it becomes 2 by 9, and similarly it is remain 2 by 9 after that, because delta is only defined at 0, so it becomes 0 after that, so you are left with 2 by 9. So it is 2 by 9 for, let me rewrite it, sorry, it is 2.9 till the range that is between 0 and 3, so up to 3 it is 2 by 9. So this is the way you can plot the CDF. Now the last thing that we can calculate for the previous example is the expected value. So as we know that it is minus infinity to infinity y PDF of y dy. So just plug in the PDF value, that becomes minus infinity to infinity, and PDF was if you remember y times delta y of 3 and plus 2 by 9 dy. So when we do the multiplication, so it becomes minus infinity y times delta of y divided by 3 dy and plus minus infinity to infinity at 2 by 9 y dy. So when we solve this equation, so when we take the derivative, so this will give me the, when we integrate it, so it becomes dy becomes a unit step. So when we take the integral of y from minus infinity, it becomes 1 by it becomes 0. Why? Because it becomes 1 by y. Take the integral of y, it becomes y square, and you have to put from minus infinity to infinity. So plus 2 by 9, so you have y square by 2 from 0 to 3 it is defined. Okay, so delta is defined only at one step, so because this is multiplier of delta, you have to just plug in the values directly in y. So multiply by delta, so it will take it to single value. Let me rewrite this thing, sorry. When we take the, it becomes y at this range, that is from minus at 0. Okay, let me write one thing, do not confuse yourself. If we have minus infinity to infinity, y times delta of y divided by 3 dy, so this becomes the value at delta y. We have defined delta y is defined as 0, so this becomes value of y is equal to 0, so that is 0. So that's why this part becomes 0. So this means that expected value of y at first part is 0 plus, take the next part, that becomes 2 by 9 y square divided by 2 and minus, because this is defined, this range is defined from 0 to 3, so instead of minus infinity, just plug in the range, that is 0 to 3. Now plug in the values, so you get 2 by 9 times 9 by 2, so that becomes 1. So this is the value you can calculate using delta function. Okay, now there are a few points before going further. First point is that x always has a CDF, that is fx of x, that is equal to probability x is less than x. So this is the first point. Second point that you need to know, that if your CDF is piecewise flat, with discontinuities, discontinuous jumps, then x is discrete. So this is one thing to know, that you have a random variable discrete or a continuous. Very easy, just look at the CDF. If your CDF is has the jump and flat, so this means that this is a discrete random variable. So similarly, if your CDF is continuous, is a continuous function, then x is continuous. Next point, which is important, if your CDF is a piecewise continuous function, with discontinuities, then x is mixed. X is mixed. So the main idea is, if you have a continuous and discrete both, then you can say that this is a mixed random variable. And the last point, you must know that when x is discrete or mixed, the PDF fx of x contains one or more delta function. So the main idea is that if you have a mixed random variable, so this means that you have few delta functions, but if it is discrete, so this means all PDF contains the delta function. Now to look at further, to clarify our concept, let's do a quiz here. Quiz 3.6, and quiz says that the cumulative, the CDF of random variable x so it is given to us that CDF is 0, CDF is x plus 1 divided by 4 and 1, and it says that 0 when x is less than minus 1, and it says that this continuous function is defined between 1 and x, and after that is greater than 1. So this is the basic idea. Now let me, the question is sketch the CDF. Now how we do that? Let me sketch here. Now assume that this is my CDF. Assume this is 1. Assume this is 0. Now it says that this is 0 when till minus 1. So assume this is minus 1, so it is 0 till minus 1. Very easy. Now minus 1 and 1. Now let's assume this is 1, and after 1 is 1, so assume this is the point, and after 1 is 1. So it's very easy. Now we have to make a function in between these. So it says when you put minus 1, so it becomes 0. So when you put 1, it becomes 1 by 2. Okay, so it becomes 1 by 2. So this means that at 1 it is stop here. Sorry. So if I take the half here, somewhere here, so this is the point at 1 by 2. Because I just plug in the 1 here in this relation, and it becomes 1 by 2. So it will go till here, and at 1 again it is 1. So this is the CDF. If I look at the CDF, and Just look at the important points that we note. So look here. So we have a continuous function and we have a jump. So this means that this is a mixed random variable. Okay, because this is a jump here, so it means that this is a mixed random variable. Now question 1 is that now question 1 says that calculate the probability of x is less than or equal to 1. This is my question number 1. So how we calculate the probability that is x is less than equal to 1? So as we know that we can write it as pfx of one. Okay, by the definition as we discussed in previous slide. Now we plug in the values of CDF of 1 is 1 actually. Okay, so it is very straightforward and it's come out to be 1. Now we have to look at the second one, and it says that probability of x is less than 1. Now less than 1. So this means that we have to calculate probability from negative side. Okay, so from negative side, if we look at, if we reach CDF from negative side of 1 is 1 by 2. Third one says that probability P of x is equal to 1. So probability at equal to 1 means that we have to write the CDF of 1 plus minus CDF of 1 minus. So as we know that 1 plus is 1 minus 1 by 2, that becomes 1 by 2. Now the last one says that calculate the PDF. So how we do the calculation for PDF? So we have to take the derivative. Now if we take the derivative of 0 is 0, so no need to write anything. Derivative of 1 is 0. Now we have to look at this range, that is I wrote range here is between -1 is less than, sorry, space is less. So what I do here, I just take this to the next page. Now the fourth part is x of x. So how we do that? We just take the derivative. So the important range that we need to calculate the derivative is between -1 and 1. Otherwise we know that this is straightforward is 0. We just put 0 here. Now for this case the main idea is to take the derivative. When we have the function in this for CDF as x plus 1 divided by 4, we have to take the derivative. Okay, so this is the main idea. Now it becomes 1 by 4 plus, we have a delta of x divided by 4. So this is the basic idea. So means that this becomes so if we take the derivative, so this becomes because there's a jump, so let me rewrite here. Let me okay, let me go to previous one. So the main idea here is that there's a jump here. Okay, so this jump is very important. This jump is represented by 1 by the epsilon. So before that we have this representation, we take the derivative of this function, that is x plus 1 divided by 4. So this is at 1. So this means that if I want to write it, I say that x equal to 1, because at 1 we have a jump, and jump is of delta x minus 1 divided by 2. Why? Because look here, we go there, this is a jump of 1 by 2 between these two. Now before that we just take the derivative of x plus 1 divided by 4, take the derivative of x. Now this becomes 1 by 4, because derivative of 1 is 0. So this will make more clarity. Otherwise, if you include delta in between, this will confuse yourself. So look at separately solve for jump and then the derivative. So it becomes 1 by 4. So this is your what you say, CDF. Now let me draw the CDF here. So CDF becomes x equal to 1, and let's suppose this is minus 1, this is 1. So at 1 is 1 by 2, otherwise 1 by 4. Let's assume this is 1 by 4. At 1 is 1 by 2 delta. Yeah. So this is the basic idea. Let me stop this. We will continue further in next lecture.